Good morning, students. Welcome to video lecture class for the subject Control Engineering. We'll continue with the problems on board plot. So the statement is the open loop transfer function g of s equal to k divided by s into s plus 2 into s plus 20. Construct the board plot and determine the first one is limiting value of k for the system to be stable. Second one is value of k for gain margin to be 10 dB and value of k for phase margin is to be 50 degree. So here also the k is unknown. For the different three types of condition, what will be the value of k? That is the question which he has asked. So the first step is you need to convert the given transfer function into time constant form. That is g of s into h of s is in the time constant form. We can write it as, so I will take 2 from this and 20 from this, so it will be k by 40 divided by s into 1 plus 0.5 s into 1 plus 0.05 s, where I will resubstitute this k by 40 as a here. Then we need to construct the table. First one is the term, slope, magnitude, break frequency and cumulative slope. So here first one is unknown, that is k or a you can take. So 20 log k or the 20 log a you can take. Break frequency is 0 and there is no cumulative slope for this. Then the first term is a simple pole at a origin 1 by s. So minus 20 is the slope. Magnitude is 0 and the omega value is 1 radian per second and the cumulative slope will be minus 20. Similarly for the second pole, that is 1 divided by 1 plus 0.5 s, slope will be minus 20 and the first frequency, break frequency or corner frequency will be 2 radian per second, that is 1 divided by t1 value is 0.5 and the slope, cumulative slope will be minus 20 and this minus 20 will be minus 40. Then the third term is 1 divided by 0.05 s. So the slope will be minus 20 for that. So omega c2 will be 1 divided by 0.05. That is 1 divided by t2. So omega c2 value is 20 radian per second. And the cumulative slope will be minus 240 and minus 20 will be minus 60. After that you have to construct the phase angle table. Since there is no term in the numerator, so I will ignore that. So omega, tan inverse of omega by 0, so it will be minus 90 degree for any value of the omega, minus tan inverse of 0.5 omega divided by 1 minus tan inverse of 0.5 omega by 1 and the pi r is the resultant angle. So vary the omega value, since that 0.22, 2, 10, 20 and infinity. So for these different values of omega, calculate these terms and get the resultant phase angle. Okay. So while calculating these phase angles, you have to be very careful. So better, instead of calculating all these terms once, you construct the table. First you complete this column, then you complete this column, like that. Then only you get the resultant angle. After getting this phase angle table, you have to go for the construction of the board plot. Okay, so here first step is draw a line at 0 dB, okay, and mark a point at omega equal to 1. Then draw these lines, that is minus 20, minus 40 and minus 60 are the cumulative slope. And we have the break frequencies as 2 and 20. Okay, so first we'll draw the plot without k. So it will start from minus 20 up to this 20, sorry, up to the omega equal to 1 and it will continue up to the, so here from minus 20 to 1 and it will continue with the same inclination up to the first frequency, that is omega c1, which is at 2 radian per second. Then for the next continuation, the slope will be minus 40 up to the third frequency, that is 20 dB, so 20 radian per second. So this is up to the omega c3 value. After that it will be minus 60 only. Okay. Remember, starting from minus 20 up to this omega equal to 1, it will continue with the same inclination up to omega equal to 2. Then from 2 to 20 it will be with minus 40 slope, because from here to 2 it will be with plus minus 20 slope, and from here to 20 it will be with minus 40 slope. After that it will be minus 60. So then you need to plot the phase angle plot. So for that, mark minus 180 degree, and you have along the x-axis you have the omega values. Okay, so from those values you give the already you have calculated the constructed the phase angle table. So from that table, try to plot this phase angle plot. Okay, so join those points with the smooth curve. Now the question is, so after drawing this, the first question is, for the system to be marginally stable, what is the limiting value of the k he has asked. So here you cannot take this magnitude plot into actual plot because k is unknown here. But if you see this angle plot, nowhere in that calculation of angle, nowhere we have considered the value of k. So it is totally independent of k value. So from this we can say that we can consider the intersection of this phase angle plot with 180 degree line. So for the system to be marginally stable, the omega gc should be equal to omega pc. So at the intersection of this phase plot with 180 degree line, we will have the omega gc and omega pc. So when we are having omega gc also there, then we need to draw a vertical line up to this 0 dB line. Okay, and whatever this distance between this 0 dB and this your magnitude plot, so that distance is going to be the limiting value of the k here. So that is, from that plot we got that omega gc equal to omega pc at 7 radian per second, and 20 log a will be 28 dB upward. So from that we will get a as 25.11, and the marginal value of k will be 1004.75. Then the second one is, for gain margin to be 10 dB, what is the value of k, he has asked. So if you want to have the gain margin as 10 dB, so if you know the value of k, then we used to calculate the gain margin with the help of the phase plot, right? So that is, first we used to look for this phase plot with this 180 degree line. Then that is, wherever this 180 degree line is, wherever this phase plot is intersecting with 180 degree line, from there we used to draw a vertical line up to 0 dB. We are going to take the distance between 0 dB and magnitude plot as the gain margin. But here we should have the specific gain margin as 10 dB. So at 10 dB you draw a reference line and measure the distance between this 10 dB and this magnitude plot, that is AB. So this much shift is required to have the system as gain margin as 10 dB. Okay, so that is, first thing is you need to look for intersection of this phase plot with 180 degree line, and you draw a 10 dB line because it is given. Okay, then from this intersection point draw a vertical line up to 0 dB and measure the distance between this 10 dB line and your actual magnitude plot. So that distance is going to be the correction value. That is, from that distance you are going to calculate the k value. That is, to have the gain margin as 10 dB, 20 log a is 18 dB. That is, 18 dB shift is required. So from that you will get the A value as 7.943 and K will be 317.7 for having the gain margin as 10 dB. Similarly, the next one is to have the phase margin as 50 degree. So here we used to look for the phase margin based on the intersection of this magnitude plot with the 0 dB line. But here we should have the phase margin as 150 degree. So for that reason, what you do, first you draw a line at 50 degree from 0 dB line, sorry, from 180 degree line. Okay, so it is plus 50, and look for the intersection of this reference line with the phase plot. From there you draw a line up to 0 dB line. Okay, and you will get the difference between the magnitude plot and 0 dB line. So that distance will give you the K value to have the phase margin as 50 degree. That is, to have the phase margin as 50 degree, 20 log A will be 4 dB. That is 4 dB shift is required to have the phase margin as 50 degree. That is the meaning here. So A will be 1.58, but K equal to 40 into A. So K value will be 63.39 to have the phase margin as 50 degree. Then the next one is, for a system G of S into H of S is 242 into S plus 5 divided by S into S plus 1 into S square plus 5S plus 121. Sketch the Bode plot and find omega PC, omega GC, gain margin, phase margin, and comment on its stability. So the first step is what you need to arrange the given function in time constant form. So for that I will take 5 from this as common. So it will be 1 plus S by 5, and in the denominator this is in standard format, and this one is, we need to compare this one with the S square plus 2 zeta omega n into S plus omega n square. So I will take 121 as the common from this. So I will get this. Okay. So as this G of S into H of S includes a quadratic pole, this is a quadratic pole here. So comparing it with the standard equation, that is 1 divided by S square in plus 2 zeta into omega ns plus omega n square. Then by comparing we need to decide the value of zeta and omega n. So that will be 1 divided by S square plus 5S plus 121 equal to this one. So from this, if you compare these two equations, omega n square will be 121. From that, omega n is 11 radian per second. And this 2 zeta into omega n will be 5. So here we know the value of omega n. So zeta will be 0.22. And you need to calculate the correction factor. Whenever you are having a quadratic pole or quadratic zero, you need to have the calculate the correction factor. So it is given by minus 20 log root of 4 zeta square, or you can write it as minus 20 log 2 zeta, where zeta is 0.22. Substitute that, you will get the correction factor as 7.13 dB. And what is the use of this correction factor will come to know when you construct the Bode plot. After that, you need to construct this table. First one is term, second one is slope, magnitude, break frequency, and cumulative slope. So first one is K value is 10. So 20 log K will be 20 dB, and these values are none. Then the one pole is at origin, whose slope will be minus 20 and whose frequency will be 1 radian per second, and cumulative slope will be minus 20. Then the second pole is 1 divided by 1 plus S. So the slope will be minus 20. First frequency will be 1 radian per second, first break frequency, and the slope is minus 40. Then I am considering a 0 here because its frequency is 5 radian per second and the last frequency is 11. So as I said in the previous problem, in this break frequency column it should be in ascending order. Based on that you write the terms here. Okay. So for that, omega C2 will be 5 radian per second and cumulative slope will be minus 40 plus 20 because it is a 0. So plus 20, it will be minus 20 will be the slope. Then for this, minus 40 will be the slope because it is a quadratic pole. So minus 40 minus 20 will be minus 60 is the cumulative slope, and the frequency is break frequency is 11 radian per second. After that, you need to construct the phase angle table. For that, we are having a 0 there, so tan inverse of omega by 5, and remaining poles with negative sign. Vary the omega from 0.1 to 20 and at last infinity. So here randomly you can take, but while taking these values, try to take the values of the break frequencies. Okay, then you calculate the respective phase angles, resultant phase angles. After calculating these things, you should go for the construction of the Bode plot. So for that, so this is the construction. So first 0 dB line. Okay, then mark a point at omega equal to 1. Draw a line from 20, 40, 60. Then you need to shift this point on the magnitude line. So the magnitude value is 12 dB. So at 12 dB, you draw one more line. Sorry, at 12 dB, you draw one more line. Is the magnitude here 20 dB, not 12. So at 20 dB line, you shift this point. That means the starting from this end up to the point which is on this magnitude line will be the 20 slope only, and it will continue up to the next break frequency with the same slope. But here the omega C1, that is first break frequency value, is also 1. So from here to here the slope will be minus 20. Then the second break frequency is how much here? The second break frequency is 5. Okay, so from 1 to 5 it will be with minus 40 as the slope. Okay, so from 1 to 5 it will be with minus 40 as the slope. After that, minus 5 to 11 it will be with minus 60 as the slope. So the plot is starting from this point, it will be with minus 20 as the slope up to the first frequency, break frequency, that is omega C1 equal to 1 radian per second. After that, from omega 1 equal to omega C1 equal to 1 to omega C2 value is 5. So from there to there it will be with minus 40 as the slope. Then from second break frequency to the third break frequency, that is from 5 to 10, it will be with the slope of minus 20. After that third break frequency, that is after 11 as the break frequency, it will be with minus 60 as the slope. Okay, and here one thing we have calculated, that the correction factor as 7.13. So at 7.13, we need to mark here 7.13 dB. Okay, and the frequency is 11 for that. So near to that point you need to give some excitation, then you need to continue with the slope, respective slope. Only that is the difference while drawing the plot if you are having the quadratic term in your transfer function. So if you are having the quadratic term in your transfer function, you need to calculate that correction factor, and that correction factor you need to mark here, and the respective frequency value is 11 radian per second. So you, while drawing the plot, you draw as in the normal procedure. Only when you come near to that omega equal to 11, there you need to give the excitation, where this distance will be 7.13. Then you continue with the respective slope. After that, construction of the phase plot. So you have the different values of omega and their respective angles. So mark those points and join those points with the smooth curved line. Then you need to calculate the gain margin. So to calculate the gain margin, you have to look for the phase plot where exactly it is having intersection with 180 degree line. So here it is having 180-degree line. So draw a vertical line till the 0 dB line and as well as this omega line, that is x-axis. So the distance between your angle plot and magnitude plot and this 0 dB line will be your gain margin, and the respective frequency will be omega PC, that is phase crossover frequency. Similarly, look for this magnitude plot intersection with 0 dB line. So here it is having intersection with 0 dB line. So from there you draw a vertical line till 180-degree and extend the same line with the same inclination up to omega line, that is x-axis. So the distance between this phase plot and this 180-degree line will be the phase margin, and the respective frequency will be gain crossover frequency, that is omega GC. So in this case, your omega GC is 3.1 radian per second, omega PC is 10.1 radian per second, and gain margin is 11 dB and phase margin is 46 degree, and the system is stable. Okay, so here the only difference is if you have the quadratic pole or 0, you need to calculate the correction factor and you need to give that excitation near to that respective frequency. Okay, so these are some of the varieties of problems on Bode plot. So basically there are three types of problems you may get in your exam. First one is with a known k value. Okay, in the transfer function k will be given, and with the simple poles and the simple pole at the origin, or say with the simple zeros. So there you need to calculate gain margin, phase margin, omega GC and omega PC. Then the second type may be k will be unknown. Okay, and for that, to identify the value of k, he may give you the conditions like if the system is say marginally stable, that time you have to take the condition as omega GC equal to omega PC, which was solved the earlier problem. Otherwise, we will give the specific value of the gain margin. To have that much of gain margin, what will be the value of k, or we will give the specific value of phase margin. So to have that much value of phase margin, what will be the k value? Okay, so this is the second type. And the third type is if you are having the quadratic terms in your transfer function, you need to identify the value of correction factor, and you have to consider that correction factor value near to that respective frequency. Otherwise, rest all things will remain same here. So the most of the time he will not give you the value of k, he will ask you to calculate the k for the specific value of gain margin or phase margin, or he may say that the system is marginally stable. In that case, you have to take omega GC as omega PC, and on the phase plot only you have to get the value of omega GC and omega PC and the value of k there. That is in the last problem we have solved. Okay, now we will try to see what are the advantages of these Bode plot. So as you have already studied the Bode plot, so the first advantage is it shows both low and high frequency characteristic of transfer function in a single diagram. Okay, for both higher level and lower level frequency characteristics. Then the second one is the plots can be easily constructed using some valid approximations. Whatever may be the value, by doing some approximation we can easily plot the graph. Then the third one is relative stability of the system can be studied by you calculating the gain margin and phase margin from the table, from the plot. So once you construct the Bode plot, it is very easy to calculate the gain margin and phase margin. So based on that, it is very easy to study the relative stability of the system. Then the fourth one is the various other frequency domain specifications like cutoff frequency and bandwidth can be determined. So from this plot you can determine the cutoff frequency or bandwidth. Okay. Then the fifth one is data for constructing the complicated polar and Nyquist plots can be easily obtained from the Bode plot. So there are another methods like polar plot or Nyquist plot. So there some of the data it is very difficult to construct by using those methods, but here it is very easy here than comparing to those methods. Okay, so any type of or any complicated given function, you can easily construct the Bode plot. Then the sixth one is the transfer function of the system can be obtained from the Bode plot directly, and it indicates how the system should be compensated to get the desired response. The eighth one is the value of system gain K can be designed for the required specifications of gain margin and phase margin from the Bode plot, as we have solved the last problem. So there, based on the required or based on the specific value of gain margin and phase margin, you can design the value of K here. Then the ninth one is without the knowledge of the transfer function, Bode plot of the stable open loop system can be obtained experimentally. So it is very useful to get the transfer function from the Bode plot with, okay. Then so these are the some of the advantages of the Bode plot. So in some of the question papers, in some of the exams, he has asked what are the advantages of the Bode plot. So in this module we have studied about the basics of Bode plot and what are the factors, how to identify those factors, and what are the specifications, that is some of the basic definitions. Okay, what is bandwidth, what is frequency ratio, and what is omega GC, and what is omega PC, what do you mean by gain margin, and what do you mean by phase margin. We have solved all the varieties of problems, how to construct the Bode plot when K is known, how to construct the Bode plot when K is unknown for the specific value of gain margin and phase margin, or how to construct the Bode plot for the system to be marginally stable or limiting to be stable, and how to construct the Bode plot for the quadratic terms also. Okay, so with this we'll conclude the fourth module, and if you have any doubt in this module, please leave the comment in the comment box. Thank you.